Hi, I'm Chris Jenner, an expert programmer at Ubisoft Reflections. I've been working on open world games for more than 20 years now, initially on Reflections Driver series and more recently on some of Ubisoft's big name brands. This talk will share some of the experience that I've gained over the years and describe a technological approach that we could apply to create worlds with deeper and more meaningful interactions for players. I'll begin with an introduction to the issues I want to talk about, explaining what I think is missing from the open world genre, and talking about how making the world itself more responsive to player actions will help to improve the player experience. I'll then present an overview of the main technology requirements for open world games and compare that with games that have large-scale interactive worlds. This will highlight the architectural problems that we have to overcome to create a viable solution. I'll suggest a set of tools that can be used to extend the current approaches to allow the open world to become an important part of the game. I'll wrap up with a summary of what's been said. For a long time, open world games have promised a living, breathing world for players to explore. Over the years, worlds have got bigger and more complex. Developers have put a lot of effort into ensuring that there are many different things to do in the worlds. However, many players still complain that the worlds feel empty. Modern action games are great at providing complex and detailed representations of player interactions with locations within the world. However, this depth disappears when the player moves from one place to another. The new locations are pristine, and returning somewhere normally means the effects of previous actions have been removed as if they'd never happened. The stories that drive our players forward through the world tend to be linear narratives, and the players must move through the world to find the opportunities to move that narrative forward by performing particular actions. This naturally means that these interactions are pre-planned, heavily scripted, and limited in number. Many games add extra activities, side quests or replayable challenges to try to counteract the empty feeling. While these can extend playtime for the game without a huge amount of developer investment, they're unconnected from the main story and often feel unnecessary. As we move into a new console generation and we begin to access the power of cloud computing, I think the time is right to re-evaluate open world games. I think we can do better and create worlds that change in response to player actions. We should make the world itself a vital part of the gameplay experience. Emergent gameplay refers to complex situations in games that emerge from the interaction of relatively simple game mechanics. This concept is vital to the sandbox feel of many games, where players are empowered to investigate different approaches to problem solving. When a player enters a camp in Far Cry, for example, the NPCs will react to the actions of the player. But at the same time, they are also reacting to the actions of other NPCs and to environmental effects. Adding in reactions to wild animals, explosions, fire, vehicles, and NPCs from different factions that may all be happening in the same environment leads to a truly chaotic effect, where a small change in initial conditions can lead to a dramatically different outcome. For many players, experiencing and learning to exploit these emergent situations can be the most enjoyable aspect of gameplay. Some genres of game are built to allow the world to be changed by the player. Think of Civilization or SimCity. We don't see the detailed character simulation, but we see large worlds which evolve over time depending on the actions of players and AI. These games look at the world on a different scale to open world action games. Rather than minute-to-minute gameplay, the turns can represent hours, days, or years. Instead of walking from one building to another, the units move from one city or one continent to the next. Actions need to be planned and their effects need to be persistent. This allows many units to work together to achieve a goal. Often players need to consider actions now that will only pay off in the distant future. As the game plays out, the players and AI will change the world by spreading out their area of control. Different parts of the world will come to life as players fight to control space and resources, and these areas of control will change as the strategic situation changes. This is a different flavour of emergent gameplay. Each game is different in ways that are hard to predict due to the complex interactions between the different combinations of static and dynamic entities in the game. Strategy and simulation games show us that emergent gameplay can come from world systems when we allow the actions to have persistence over longer time spans and direct the actions of our NPCs with a high-level plan. If we could find a way to realise similar systems within an open-world game, we would get a world that changes and adapts to the actions of the players, presenting new challenges and opportunities to the player each time they enter the world. Players would be able to interact with a small-scale simulation, giving them emergent local gameplay, but the consequences of their actions could persist through the effect on a larger-scale world simulation. If the world simulation is driven by intelligent systems that will change their plans to adapt to the changing situation in the world, then we can see a new, deeper level of emergence within our games. Creating a large-scale world simulation within our open-world games would give us several significant benefits. Changes in the world simulation can be realised in the world, altering the static state and the population of NPCs that exist in different areas. Experiencing and learning about the different larger scale mechanics will offer an extra level of challenge and fun for players. NPCs would be guided by a higher level intelligence, so they would have a purpose for being where they are and clear motivations for the actions they're performing. The world will be more coherent. These changes will be different depending on the actions of the player, so the game content will be different for each playthrough of the game. Most importantly, the player's actions will have permanence. Returning to an area that the player has visited before will be interesting, as the area will be different. Those changes will reflect what the player did when they were last there. This depth of response will give more power to players and weight to their actions. We have an idea of what we might start to create to fill our empty worlds. But how can we fit two very different styles of game into one consistent whole? I'll start to address this question by looking at the general requirements of open-world sandbox games, which support detailed small-scale simulation, and I'll compare that with games that have larger-scale simulations to identify the differences. So we'll start by looking at open-world sandbox games. The simulation that runs here is limited to a small part of the world around the player. Generally, the player will be interacting with several NPCs, each of which will be responding to the player actions and the actions of each other. Inputs are continuous. Player and NPC interactions with the state of the world are complex. The simulation has to be responsive and accurate, as the results are directly visible to the players. Many different game systems work together to create a dynamic and unpredictable environment, and interactions between different systems lead to emergent gameplay. The complex interactions of many different game systems lead to the emergence of unexpected consequences. Each of these different systems has to be realized within the world, and each system has its own complex state that needs to be evolved over time. AI needs to understand the world around it and make decisions about what to do next, driven by the actions of the player, other AIs, and static objects in the world. The AI drives an animation system for the character, and the current animation state feeds back into the AI, controlling what actions are possible. The physics system feeds into the animation system and the AI, preventing characters from penetrating the static world and performing raycasts to determine which elements are currently visible. Other systems work alongside these elements and feed into them. Depending on the gameplay requirements, we may have to consider vehicles, wild animals, fire which propagates around the world, and so on. All this simulation is very costly in terms of CPU usage. Each of these systems have to update in real time because of the requirement to draw a new frame every 30th of a second. This gives us only 33 milliseconds to perform all the calculations required to update the state of every object in the world. And at the same time, we're also preparing the data to instruct the GPU on how to draw the world. The cost of each system increases as the number of entities it has to deal with increases. So the CPU usage is normally controlled by putting limits on the number of active objects within a particular area. Typically, games would limit the number of active NPCs to be 20 or 30 at any given time. As well as limiting the number of NPCs, the simulation is typically limited in area as well. Detailed simulation requires a lot of detailed data to work with. Physics systems require collision meshes for all the objects. AI requires navigation meshes for movement and other markup in the level to identify interactable objects or cover locations. The interactable objects themselves often come with data such as animations to specify how they can be used. For a large open world game, it would be impossible to load all of this data for the entire world into memory at one time. The games rely on streaming systems to ensure that high detail data is loaded only in the area immediately around the player. This often means that it is impossible for simulated entities to stray more than a few hundred meters away from the player. The constraints on numbers of NPCs and the distance which they can be simulated from the player mean that open world games have to use a system of spawning characters in the area around the player, and deleting them when the player leaves. This creates a bubble of activity that follows the player around as they traverse the world. Some spawned characters might be significant to the story of the game, placed carefully by level designers in groups to play out a specific interaction with the player. Others may be background civilians going about their normal life. Mission-specific characters are there to interact with the player in a particular scenario, which has been pre-planned and may trigger a change in the linear narrative that the player is following. Generally, the background characters have no reason to exist other than to fill the world for the player. When they do exist, they can interact with other people and things in the area, but those interactions have no real meaning. When the player leaves and the character gets deleted, the effects of their actions are also removed and the world resets to its default state. So we've seen how open world games tend to simulate a small part of the world in high detail. Strategy and simulation games often show players a view of the entire world on a single map. They achieve this by maintaining and evolving the state of the whole world. While the state and actions of individual units are quite simple, the games as a whole are complex. The large number of units and the persistence of actions means that no two games will play out in the same way. The appearance of the world can change dramatically as one side or the other gains dominance, controlling different areas and taking over resources from the enemy. The existence of opponents to the player with complex plans of their own leads to a different kind of emergent gameplay than we saw in the small-scale simulation of open-world games. Players have to continually change and adapt their plans in response to new threats appearing or old ones disappearing as the balance of power changes. The world in these games is often large and contains a large number of dynamic entities like military units, and also many static entities such as cities, farms or factories. The state of each entity is usually limited to something as simple as a unit type, a health and location. Locations may just be grid cells. The action of the units are normally restricted to a choice from a discrete set of moves and actions that are available. In some games, the set of actions may be large and dependent on the type of the unit, but once an action is selected, then changing the state of the world to represent the action is generally easy. Moving a unit changes which cell it's in. Attacking reduces the health of the target unit. Changes to the world happen at low frequency, often turn-based. Players get the chance to give orders to their units, and then AI can give orders to each of its units. Once the orders are given, the events in the world play out according to the rules. The main complexity in implementing a system like this is ensuring that the enemy AI is strong enough to provide the player with an interesting opponent. The AI in simulation games is vital to create the emergent situations that provide interesting gameplay. The job of the AI is to select the best possible orders to give to a large set of units to allow the computer-controlled players to try and win the game. The large numbers of entities and the complexity of the interactions between them and the unpredictability of the opponent's moves make this a hard problem to solve. Lessons can be drawn from other situations where computers have been taught to play complex games, like chess. Although chess is a fairly simple game when compared to some of the larger strategy games on the market. The basic approach of creating a heuristic function which can analyse any state of the game and give it a score based on the strength of that position for a particular player is still valid. Moves can then be determined by looking at the set of possible moves and choosing the ones that give the greatest value of this heuristic score function. Adding a large-scale simulation to our open world will require us to add certain features on top of the action game architecture. We will need large numbers of interacting entities, which have to retain a persistent state even when the player is not directly interacting with them. In this section, I'll present a set of tools that can be used to achieve these goals. Some are applicable in all games, even those without a large simulation, and others will be more useful in some situations than others. The easiest way to optimize any code is to find a way to avoid running it. When we fill a large world with many entities, most of those entities will not be visible to the player. For entities that are not interacting with the player, we can choose to drop all the expensive calculations required for high detail simulation and switch to a much simpler simulation model. When the character gets close to the player, we can spawn in a high detail representation which behaves like a traditional action game NPC. So we can drop the animation, physics and complex AI for controlling those systems. We will need to retain a set of data describing the high-level state of the character, its position, inventory, appearance and so on, and operate on that data with a simplified set of code. Interactions between characters and with the environment can be described using simple logical rules rather than complex simulation. This can go a long way to fixing our CPU and data bottlenecks, as the simplified systems can be lightweight and only access permanently loaded data. Another way to avoid running code is to run it less frequently. Action games need high update rates because they need to update the movement within the scene for each frame. When we have low-LOD characters, we're not drawing them every frame, so updating at graphical frame rates doesn't serve any purpose. When the majority of our characters have a simpler state, it becomes obvious that we don't need to step the characters at the high frequency we would normally use. The AI for the character no longer has to react to a highly dynamic environment, which is changed by player actions. So decisions don't need to be updated more frequently than every few seconds. Position is an interesting part of this, and we'll speak more about this later, but reducing position updates to every second or even longer is unlikely to have any noticeable impact. Yet another way to avoid running code is to deal with a smaller set of objects. Depending on the world systems that we're simulating, it could be possible to represent a set of high detail entities as a single low-LOD entity. A simple example would be a military unit in a strategy game. In the high-LOD representation, we would expect to see a number of soldiers, each of which can act independently of each other. Generally, all the soldiers will remain close to each other and work together to perform a single task. To reduce the processing required for the low-LOD representation, we could merge all the individual NPCs into a single object. This object would have a count of the number of soldiers within it. When the unit gets promoted to high-LOD, we could spawn individual members as NPCs, each with their own properties and AI. Our system will rely on a high-level AI that can decide what the NPCs in the game will need to be doing. The heuristic AI approach that we described when talking about large-scale simulation games can be very costly to calculate, particularly when there are large numbers of active entities to consider. Entity reduction can reduce this cost significantly if the AI can plan a strategic approach by considering a smaller number of more significant compound units. The more detailed orders given to individual NPCs can be calculated by a simpler AI system following the orders of the strategic level. The AI can also run at a very low frequency. High-level plans would not need to change often. In fact, changing them too frequently would be counterproductive, as there would be no stability in the behaviour of the world. Running a costly process every few minutes can be achieved by breaking the task up and only running a small part of it every frame. We've been looking in the previous slides at approaches that can reduce the cost of updating entities in the world. But there is a way that we can avoid simulation entirely by describing a dynamic world with a static set of data. This is a technique that we used successfully in Driver San Francisco to describe the motion of all of the civilian traffic in the city. Thousands of cars were following pre-planned routes around the city, laid out in a way so that they wouldn't collide with each other. Each deterministic vehicle could be queried to return its position at any time. When the cars were near the player's position, we could spawn a real vehicle, which would follow the deterministic path. When the player was far away, the deterministic data didn't need to be touched at all, but the cars were still moving around because time was passing. This approach is very cheap in terms of CPU. Thousands of vehicles can move without any need for AI, collision detection, or vehicle simulation code to run. It is also very efficient to synchronize across a network, as there is no communication required for each vehicle. We just need to synchronize a session time between remote machines, and each client can calculate the position of every vehicle in the city. The problem with applying this approach to interactive world simulation is that deterministic entities can't react to anything. Their movements are planned before the game even begins. In our game, we handled player interactions with traffic by deleting the deterministic traffic vehicle and replacing it with a more traditional AI-controlled vehicle. A more useful application of the idea of deterministic motion is to calculate deterministic paths at runtime and assume that they can be changed if the state of the world changes. When an NPC decides that it needs to move from one location to another, it can find a path to follow and calculate how long it will take for it to reach the end of that path. This path can then be added to a set of currently active paths in the world, and the AI doesn't need to make another decision until the end time of the path. At any point, we can query the path to locate the NPC, and if it is close enough to the player, we can spawn a high LOD entity. The entity can still be free to react to events in the world, however. If the player was involved in a gunfight nearby, but not close enough for the NPCs to be promoted to high LOD, we could send messages to all the NPCs in the area and give them a chance to update their deterministic AI state in response to the new information. If that changed the behaviour of the NPCs, they could calculate a new deterministic path and start moving to a different target location. This approach is an extreme example of reduction in update frequency. Although each update might be quite expensive, we can leave entities untouched for minutes at a time as they deterministically play out the actions that they want to perform. Efficient multithreading can be a problem in game engines, as there are many dependencies between the calculations that need to be performed in a frame. We can't draw a character until its animation has been calculated, and we can't calculate its animation state until its AI has decided what it's trying to do. Low-LOD simulation has a big advantage here, in that we can break all of these dependencies. We don't need our distant characters to react instantly to changes, as the player isn't around to see any delay. This means that we can treat all of our updates as being independent of each other, and get our code to act on the current state of the world, rather than having to wait for the very latest updates to that state. Independent updates can all happen in parallel with each other, and in parallel with any other game threads, which gives us much more flexibility in scheduling this work. The work of updating our large-scale simulation can fill any gaps in the CPU usage of the high-frequency threads caused by synchronization waits. Adding large-scale simulation to our worlds will require extra processing power, and one option for gaining more power is to use the cloud. Semi-deterministic datasets are ideal for networking, as they change infrequently. This means that a low bandwidth connection can provide accurate simulation information for many thousands of entities. The assumption we made when talking about threading, that we don't need fast reactions from our low-LOD AI, also holds here, so latency is not a problem either. The cloud would be an ideal place to update our low-LOD large-scale simulation, and we could then feed that data into the player's computer for processing of high-LOD simulation. Cloud computing would allow our complex large-scale simulations to be persistent and also make them accessible to many players at once. The possibilities are endless for finding ways that many players could interact in shared, evolving worlds, where the world itself acts to change the environment even when players are not directly involved. Companies such as Spatial OS and Hadean are actively working on technical solutions to allow this sort of scenario. The approaches suggested in this talk could work cohesively with cloud solutions to reduce the costs associated with running large-scale worlds, making them a more economically viable proposition. This talk has highlighted some of the strengths and some of the weaknesses of the open world genre. The technical ideas that have been discussed show approaches that we can take to address those weaknesses and add greater persistence and depth to the actions of players as they explore our worlds. Actually implementing a system that allows us to shift the focus of gameplay onto a more persistent world has many more challenges than I have had time to address here. Approaches to narrative, level design, and art production will all have to adapt to make the most of the strengths of world-scale emergent gameplay. Moving the world itself to the heart of our gameplay will bring benefits to the player in terms of variety and cohesion of experience, and in adding significance to the choices that are made. Truly living worlds will not feel empty and lifeless. We can add this depth without sacrificing the emergent experience that comes from detailed small-scale simulation. As we move into the world of the next generation of consoles and greater processing power from the cloud, the time is right for us to give more to players by allowing deeper interaction with our large-scale worlds.